It's great to be back to Korea. Thanks to Kim Yeon, I've been enjoying various Korean cuisine, in particular the fermented fish. It was pretty much impressive. So if you guys haven't tried it before, then I strongly recommend you to try during this school, if you have time. Okay, so what I'm going to talk about in this set of lectures is some introduction to integrability and its application to N=4 supermil theory. So this is the outline of my lectures. And in the first and the second lectures, I will give some introduction to what the integrability is and how the integrability can be used. And in the second and the third lectures, I'm planning to talk about the relation between integrability and 4D N=4 supersymmetric Yang-Mills theory. So the integrability is usually regarded as something that can be used for analyzing two-dimensional systems. But the point is that you can actually use those techniques to study four-dimensional N=4 supermil theory. And in the first lecture, if I have enough time, then I want to talk a little bit about what's called ODE-IM correspondence, which is essentially how the integrability shows up in the study of one-dimensional Schrödinger equation. And this topic has, well, it's very interesting. It has many connections to various different areas of physics. For example, I believe it has a deep connection with the resurgence about which Gerald is going to talk about. And also it has some connection with things like wall crossing. Okay, so that's the plan of my talk. And so let me start. So the first topic is introduction to integrability. So let me start my lecture. Okay, by the way, before I start, I prepared some problem sets or exercises, and I put it in the webpage of Kavli as in Winter School. So if you're curious, then you can go to the webpage and then see the problem sets. So maybe like if you try to solve it after my lectures, then it might be useful for you. Okay, so let me start my lecture by asking this question. What is integrability? So in the case of classical mechanics, classical or quantum mechanics, instead of field theory, then there is actually a well-defined answer to this question, which is called Liouville integrability. And essentially, in the case of classical and quantum mechanics, integrability means that the number of conserved charges is equal to the number of degrees of freedom. So this is called Liouville integrability. And the most well-known example of this Liouville integrable system is, of course, the harmonic oscillator, whose Hamiltonian is essentially, okay, so let's consider multidimensional harmonic oscillator, whose Hamiltonian is, for example, given by this form, 2m over b squared plus 2 over m omega k squared x k squared, and of course, like a p and k are canonical conjugate. And in this system, as you all know, that in addition to the full Hamiltonian, you can define the conserved quantity, which is essentially the Hamiltonian for each direction. It's essentially just given by this expression. And as you can see, there are as many conserved charges as the degrees of freedom. So this is a canonical example of the integrable system. And on the other hand, there is also a well-known example of non-integrable system, which is, for example, the system which exhibits chaotic behavior, something like a double pendulum. So this is something like this. So you have pendulum, and then you have another pendulum. Okay, I'm not sure if this picture was useful, but anyway. So this is the definition of the integrability in finite-dimensional classical mechanics or quantum mechanics. So now you can ask, what is the definition for quantum field theory? Is there any notion like integrable quantum field theory? So the question that I want to ask is, what is the definition for QFT. And as we all know, the quantum field theory has infinitely many degrees of freedom. So the natural, if we want to have a natural extension of the notion of integrability to quantum field theory, it seems like you need infinitely many conserved charges. Okay, so this could be a kind of like a, well, working definition of integrable quantum field theory, but at the same time, this definition is a bit too abstract and you don't quite know what the physical consequence is. So this definition is a bit abstract. And I don't know what is the physical consequence. But it turns out having infinitely many conserved charges have a very well-defined important physical consequence. So that's, let me start my lecture by explaining this, the physical consequence of infinitely many conserved charges. So now I'm going to discuss the physical consequence. To discuss that, let's discuss some 3-to-3 scattering. So as you all know, the S matrix is one of the basic observables in quantum field theory. So you have something happening here, and then you have the particle P4 going out, P5, and also P6. So this is the 3-to-3 scattering. And also, to simplify our discussion, I'm going to consider non-relativistic quantum field theory. Or you can think of it as some kind of non-relativistic limit of relativistic quantum field theory. Okay, so far so good. And what do we know about this 3-to-3 scattering? One thing we know is that in general quantum field theory, we know that there should be momentum conservation, which means that if you sum the momentum Pi from 1 to 3, then it should match with the sum of the momenta for the outgoing state, right? And another thing we know is the energy conservation. So here I'm talking about non-relativistic quantum field theory. So essentially the energy is just given by P squared. So in addition to this, in addition to the momentum conservation, I also have this equation. Okay? So this is always true, like even for non-integrable quantum field theory. So now the question I want to ask is, what happens if you consider integrable quantum field theory? And our working definition for integral quantum field theory is the quantum field theory with infinitely many conserved charges. So let's suppose that there exists the charge Q n for any n integer. And let's further assume that the action of this charge on this like asymptotic state is given by this expression, Pi to n, P1, Pn. So this is the generalization of momentum and energy, and this kind of behavior is what you expect if the theory has higher spin conserved charges. So the momentum is the spin 1 current, and the energy is like a spin 2 current. And if you have a higher spin currents, then the action of the charge constructed out of that current typically takes this form. So let's assume that there exists such conserved charges. Now, one immediate consequence of the existence of these conserved charges is that now we have infinitely many conservation law, and in addition to momentum energy, and that immediately tells you that one immediate consequence is that the set of incoming momentum must coincide with the set of outgoing momentum. Of course, this is an obvious consequence because otherwise there is no way to satisfy the conservation law. But this is a bit too kinematical and it's not so interesting. And actually, there is yet another more interesting consequence of the existence of integrability. And to understand that point, let's properly consider the scattering process. So if you read a textbook, of quantum field theory, I think most of the textbook defines the wave packets in order to really define the scattering process. So let's try to do also here. So consider a wave packet. And essentially, the wave packet means that instead of like a plane wave-like state, we consider some integral over dp, and I assume that, so I have some Gaussian factor, and then like average over this Gaussian factor. So this, and I assume that, well, C is sufficiently large so that the wave packet is localized. And considering this kind of wave packet is essentially equivalent to considering the wave function. So this is equivalent to considering the wave function of this form. So you have dp and E minus C p minus pk squared. And then there is a wave function for each p, which is averaged over. And that wave function is given by exponential and minus 2m I h bar times p squared times t. So this is the phase coming from the propagation of the energy, propagation in time, and then there is a plane wave factor. So this is just the definition of the wave packet. And of course, this is just a Gaussian wave, Gaussian integration. You can, well, try to perform the integration and then see where the peak of the wave packet is. But of course, like there is a simpler way to analyze where the peak of the wave packet is. So the simpler way is to denote this phase factor by f of p, and then look for the following equation. So the peak of the wave packet is given by del p. So essentially, the peak of the wave packet is given by the stationary phase, the position of the stationary phase. And I need to evaluate this equation at the position p equal pk, because if you go back to the previous slides, then you see that there is like a Gaussian wave function, the Gaussian factor, which is here. And I assume that the Gaussian factor is concentrated enough around pk, p equals pk. So essentially, the peak of the wave packet is determined by this equation. And if you solve this equation, then, well, it's just an easy exercise. And then if you do it, what you get is this expression. So the peak of the wave packet is determined by this equation. And as you know, this part is precisely the the velocity of the particle, classical velocity of the particle, and it kind of matches our classical intuition that the wave packet travels along the classical trajectory of the particle. Okay, so this was just a review of the wave packet, and now I want to consider the consequence of the conserved charges. So the idea is to now act this generator, so exponentiated generator, which I denote by I alpha n qn, where qn is the one I defined before. And so the idea is to act this generator to the state P, to the wave packet P, and see what happens. And so the definition of Qn is that if Qn acts on the plane wave state, it produces some P to N. So essentially, if you act this factor or this generator to the wave packet, then this f of P gets shifted because of the action of the generator. And it's shifted by this amount. Because the action of Qn is just P to N. So now I can play the same game of finding the peak of the wave packet after shifting f of P by this amount. And this leads to some interesting observation. So let's find the peak. And if you calculate the peak, then what you get is, again, this is the ordinary part coming from the original f of P. And in addition to that, you have n times alpha n times P to n minus 1. Sorry, this is k, because I need to evaluate this equation at P equals pk. So this determines the position of the peak. So let's first set n equals 1. If you set n equals 1, you can see that the shift is actually independent of the momentum. And it basically means that the shift is just like a shift of x. Well, this is, of course, very natural, because if you set n equals 1, q of n becomes momentum. And the action of momentum or translation is just the shift in the x direction. And then we can also ask what is n equals 2. N equals 2 is also easy because, okay, in the case of n equals 2, of course, the shift depends on pk. Well, it actually depends linearly. But you can see that that shift can be absorbed into the shift of t. And so now this is the shift in t. But this is, again, very natural because we know that n equals 2 corresponds to energy. Is this clear? But something interesting happens if you start considering n larger than 2. If you consider n larger than 2, then you discover that the shift of the trajectory depends on pk, the momentum of the particle. So in particular, if you consider several particles, then the shift of each particles are actually different. And by using that, you can actually shift the trajectories of the individual particle by arbitrary amount. So this leads to a very important consequence. So let's again draw a picture of 3 to 3 scattering. So now I'm considering integrable quantum field theory. So as I said, because of the charge conservation, the incoming momentum must be the same as the outcoming momentum. And so let's take some nice combination of these higher conserved charges. And so that, for example, this trajectory of the particle 1 moves in this way. No, in this way, so in the opposite way. And this particle 2 moves in, for example, this way, and the particle 3 moves in this way. Then you can separate the trajectory of the individual particle very much, so that actually each particle only scatters one by one. So now I have P1, P2, and P3. And because P1 is far away from P2 and P3, what happens in this process is that P2 and P3 first scatters, and then afterwards P3 meets P1, and then P1 finally meets P2. Yeah, that's a good question. I forgot to say that. So Okay, let's now say we are in 1 plus 1D. So in that case, I can do this, right? So everything is just plain, and I can just like move the trajectory by arbitrary amount. Okay, so this leads to an important consequence. So originally, what was happening in the middle was something like a mess. But now it turns out that actually scattering, only 2 to 2 scattering happens at one time, and which means that actually 3 to 3 scattering, you should be able to write it as some product of 2 to 2 scattering. So this means that the 3 to 3 amplitude factorizes into 2 to 2 scattering amplitudes. Okay, and there is yet another important consequence. So when deriving this equation, I use a particular set of conserved charges, but I can also choose another set of conserved charges, now moving P1 in the opposite direction, P2 and P3 also in the opposite direction. Then the final expression, the final picture that you get is slightly different. So now the picture that you get is something like this. So P1 and P2 first meet, and then later there appears, there is a scattering between P1 and P3, and finally there is a scattering between P2 and P3. And this is very important because we assume that our theory has the higher conserved charge symmetry, and which means that this picture here must be the same as this picture here. So we should actually relate these two pictures by equality. And this is precisely what is called Mbox equation. Which gives a very important constraint on the 2 to 2 S matrix. And I should emphasize that this is actually very, very non-trivial equation. And the reason is, suppose your particle comes with some label, and the label runs from 1 to n. Then 2 to 2 S matrix has like 4 labels, because you have 2 incoming particles and 2 outgoing particles, and each label runs from 1 to n. So there is like n to 4 degrees of freedom in the 2 to 2 S matrix. On the other hand, let's ask how many Mbox equation you can write. So to write down the Mbox equation, you need to have 3 incoming states and 3 outgoing states. So which means that the Mbox equation, there are actually n to 6 Mbox equation. This clearly tells you that the Mbox equation is actually over-constrained system, and it's actually surprising that the solution to this equation exists at all. And in the case and this also tells you that if the solution exists, then like the Mbox equation should be very powerful. Okay? So this is how the existence of higher conserved charges is related to some very important property of the scattering. In particular, 1 is the factorization of the S matrix, 2 is the Mbox equation. So now the next topic is to understand, well, to see how to really use this kind of equation to really solve some like a non-perturbative quantum field theory. But before moving on to that topic, is there any questions so far? Yes.
What is the counting of n to the power 4?
N to 6?
N to the power 4.
N to the 4. Well, so each index, so do you agree that there are 4 index if you consider 2 to 2 scattering?
Yeah.
Then each index runs from 1 to n, and so you have n times n times n times n.
Okay, thanks. And one more question. So to define integrability of a quantum field theory, is it necessary to have a well-defined S-matrix notion? Because, for example, in CFT we will not have S-matrix.
In the CFT you don't have the S-matrix, but through my lectures I'm mainly concerned with massive quantum field theory.
Yeah, but like in any non-trivial manifold, S matrix may not be well defined.
In the non-trivial manifold,
Huh.
I don't have a good question to that. Yeah, well, you need to, well, of course, in ADS, for example, there is a nice analog of the S matrix, which is the boundary correlators. But I think, I'm not sure if there is any general story which applies to general manifold. I don't know who decides.
Okay. If we consider a higher dimensional, higher point correlation functions for 4-to-4 S matrix, is it also can be factorizable to
Yes,
lower dimensional ones?
yeah, if there exist infinitely many conserved charges. Yes.
Then for 3-to-3 case, we have two ways for factorization,
Right.
and there can be many ways.
Right.
Okay, thank you.
Yeah.
Yeah. Hello. Does every Yang-Box equation is linearly independent?
The question is whether the all the Mbox equations are independent or...
Yes.
I think, well, of course, we know that the solution exists. So in that sense, I should say it's secretly, well, but I think in general, it's independent. It's all the constraint system, and it's independent, but sometimes there exists a solution.
So how about the 4-particle scattering? Can we give further Yang-Box equation?
I believe you don't get any further constraints.
Okay.
Because once you factorize everything into 2-to-2, I think Yang-Box is the main, the only thing that you need to worry about.
So these conserved charges generally conform to some global symmetries of the theory. So how are we getting infinite number of conserved charges?
Sorry, what is
how are we getting infinite number of conserved charges?
How do I get?
Yeah,
okay,
what are the corresponding symmetries?
I'm going to explain that.
Oh, okay, thank you.
Well, tomorrow. Okay, so now let's see how to use the Mbox equation. So the model that I chose is the ON nonlinear sigma model. And, okay, so what is ON nonlinear sigma model? So it's the sigma model with target space. Okay, so sorry, I also need to say that it's again 1 plus 1D. Target space S n minus 1, so higher dimensional sphere, and which means that the field that appears in the Lagrangian is some n-dimensional vector, and it depends on z and z bar. These are like a 1 plus 1D coordinate. And satisfies this constraint. And what I want to do today, in the rest of my lecture, is to determine 2-to-2 S matrix of this system, ON model. And the main idea that I employ is, in a sense, the bootstrap philosophy. So what I mean by the bootstrap is to use some inputs, some concept, and then feed that input into some consistency equation and determine the final answer. So that's the idea of the bootstrap, and which is also true in the conformal bootstrap. Here, I'm not using conformal bootstrap, but the philosophy is basically the same. Okay, so now let me be more specific about the theory that I'm considering. Okay, let's go to the next page. So So the partition function of this ON model is given by this path integral. And so let's put some coupling constant here, and then I have some Lagrangian here. And the Lagrangian is, of course, given by very simple expression like this. But of course, when you do the path integral, you need to remember the constraints, which, this constraints. And one simple way to take into account the constraints is to introduce Lagrange multiplier. So I introduce additional field sigma, and if you integrate over sigma, then you get delta function. Well, precisely speaking, you should also put I there, but okay, let's not talk about those subtleties. And of course, I need to put d of sigma here. Okay? So by looking at this Lagrangian, in particular, the version which doesn't contain sigma, you can immediately see that classically, there exists n-1 massless particles, because your target space is Sn minus 1. And then if you pick some point and then consider infinitesimal variation, there are like essentially n-1 direction. And because in the original Lagrangian there is no mass term, it seems like you have n-1 massless particles. But of course, this is actually wrong. The reason why I said of course is because it kind of contradicts what people call Coleman-Mermin-Wagner theorem, which basically states that there cannot exist Goldstone bosons. Okay, so the reason why this Lagrangian is related to the Goldstone symmetry breaking or Goldstone bosons is because this Lagrangian, you can think of it as kind of effective Lagrangian, which describe the symmetry breaking pattern SON to SON minus 1. And in that context, the massless particle that I was talking about is precisely the Goldstone bosons. But we know that such things don't exist in 1 plus 1D, so this should be wrong. And let's see why it's wrong using large N analysis. So input 1, so actually input 0 was not input, it was actually wrong, so I should write wrong in bigger letters. So input 1 is the large N analysis. So the idea is as follows. So let's go back to the Lagrangian. And if you look at the Lagrangian, after introducing sigma, now you don't have to worry about the constraints imposed on n, because it is automatically taken into account by integration of sigma. And then it's clear that the field ends appears only quadratically in the Lagrangian, which means that you can integrate out ends. So take the partition function and integrate out, and fields, and as a result, you get some path integral which involves only sigma, and you have some effective Lagrangian. So what is this effective Lagrangian? So effective Lagrangian contains one piece which was there in the original Lagrangian. So this piece basically comes from -1 here. Okay, and then there is some log determinant coming from integration over the field n. Okay, which is, of course, you can rewrite it in as trace of log. Okay. So far, I'm not taking any large N limit, but let's now take the large N limit. So here, the large n, I take the large n limit by sending n to be infinity and at the same time keeping kappa n to be fixed, which basically means I'm also sending kappa to 0. So this is a kind of analog of the two-fifth coupling constant in the gauge theory, in the large n gauge theory. And in this limit, there is something nice happening in the effective action. So if you rewrite this 1 over kappa, 1 over kappa, 1 over kappa, in terms of lambda, then you get n times n over lambda. Then it's clear that there is an overall factor of n because there is n in the first term and also in the second term, which basically means, and we are further assuming that n is very large, which basically means that, okay, maybe I should keep this a little bit more, which basically means that n is, you can use the saddle point approximation. Okay, so then let's try to do the saddle point approximation. And saddle point approximation, and the saddle point is given by 1 over equation like this, 1 over lambda equals trace of 1 over del squared plus sigma star, where star is the saddle point value of sigma. And this trace actually means essentially integration over all space, which you can convert it into integration over all possible momenta. So this is essentially this expression. And this right-hand side, this integral can be evaluated as follows. Lambda over sigma star plus 1. So what is lambda? So this lambda, oh, I don't like this color. Okay, well, there is no way. This lambda is the UV cutoff. So as you can see, this integral is logarithmically divergent because there is like a p squared in the denominator and the and p d to p in the numerator. And so I need to introduce some logarithmic, some cutoff. And if you rewrite this equation, then what you get is that the sigma star is lambda times e to minus 2 pi over lambda. So as you can see, this 1 over e to minus 1 over lambda is very non-perturbative. So it doesn't have any nice expansion around lambda equals 0 limit, a nice perturbative expansion around lambda equals 0 limit. So this is basically telling us that sigma gets a VEV because of some non-perturbative mechanism. And what is the physical consequence of having sigma star? Well, having sigma star? Well, to understand that, I need to go back to the original Lagrangian, so this one. And then you can see, actually, sigma appears as a mass term for the field n. So once sigma gets a VEV, which then it means that sigma star non-zero basically means, because of this term in the original Lagrangian, you have actually all the field n becomes massive. And in particular, there are n massive particle. So which is quite different from what we concluded by just doing the classical analysis, because in the classical analysis, we concluded that there are like n minus 1 massless particles, but actually because of some non-perturbative mechanism, we have n massive particles. So the input 1, let's write it again. So the consequence of the input 1 is at large n, there are n massive particles. And I actually, in the rest of my lecture today, I actually assume that this is true also. finite n? Well, of course, this is a conjecture, but the idea of the bootstrap is assume something reasonable and see whether we get a reasonable answer or not. Okay, then input 2, I claim that there exists infinitely many conserved charges in this system. I didn't explain anything about this point, and I'm going to explain this tomorrow. And in particular, in this ON model, you can actually argue that even quantum mechanically, there exists infinitely many conserved charges. And that's what I'm going to explain tomorrow. Yes, finite n also. Well, you can actually argue that the existence of infinitely many charges. Okay, so the idea is to use these inputs and then try to determine the 2 to 2s matrix. But I should say, before doing that, I should say that because of what I explained in the first half of my lecture, the existence of infinitely many conserved charges immediately implies the Mbox equation. Okay. All right, so is there any questions so far? So now I'm going to bootstrap this matrix. So as I said, what I want to understand or what I want to determine is the 2 to 2s matrix. So let's review, let's first discuss the kinematics. So 2 to 2s matrix is something like this. So you have momentum P1 incoming and P1 outgoing, P2 incoming and P2 outgoing. And as I argued, if you consider the non-perturbative mass generation, this ON model have n massive particles. And so which means that each particle comes with index n. And I, j, k, l runs from 1 to n. And correspondingly, the S matrix has 4 indices. And of course, and as we all know, the S matrix is a function of Mandelstam variable. For example, Mandelstam S variable is given by P1 plus P2 squared. And Mandelstam T variable is P1 minus P2 squared. So normally, if you consider 4-dimensional quantum field theory, there is yet another Mandelstam variable, which is U variable. But in 1 plus 1D, actually it turns out there is no U variable, or U variable is always 0. And you can actually show that just S and T satisfy this equation. Well, this is actually very easy to show by using this definition. And okay, so I also assume that mass of the individual particle is m squared, which is essentially determined by the expectation value of sigma. Okay. So now let's talk about some analytic property of this S matrix as a function of Mandelstam variable S. So what do we know about the analytic property of the Mandelstam variable, well, of the S matrix? So let's draw a picture. So as a function of Mandelstam variable S, we know that the S matrix contains a branch cut starting from 4 times m squared. So this basically corresponds to 2-particle threshold. So if the energy is larger than 4-particle threshold, then you can produce on-shell particles at the intermediate stage. So that produces the branch cut. I think you are familiar with this fact from the a Feynman diagram computation. And there is also another branch cut, which essentially corresponds to particle production in the T channel. So here in 1 plus 1D, there is only S channel or T channel, and both channels in principle can produce onshore particles, and this starts from 0. Right. So, and the physical S channel scattering is here, because if two particles have physical momentum, then typically, well, of course, the sum of the energy of these two particles is larger than 4m squared. And if you also take into account I ipsum prescription, you can say that actually the physical S channel scattering corresponds to the region above the branch cut. On the other hand, physical T channel scattering corresponds to this. And the reason why I was talking about this analytic property of the S matrix as a variable as a function of S is because I want to introduce more useful, more convenient variable, which is called the rapidity variable. So the rapidity variable is defined in this way. So you have two particles and two momentum and energy, and we know that P and E satisfies the on-shell condition. And one simple way to automatically take into account the on-shell condition is to write something like this. Then, because of the cos square minus sinh square is 1, the on-shell condition becomes automatic. And using this variable, you can also compute the Mandelstam variable S, and that is given by 4 times m squared times cos squared over theta 1 minus theta 2 over 2. And I claim that the S matrix is a function of S only, which basically means that S matrix is a function of theta 1 minus theta 2, the difference between theta 1 and theta 2. This is, of course, very reasonable because if you do the boost, if you act the boost transformation to the individual particles, then you basically shift the values of thetas by the same amount. And well, S matrix should be invariant under the boost, so that's why the S matrix only depends on the difference. Okay, so then now let's ask what is the analytic property of the theta plane? And then you can basically use this transformation rule and see which part corresponds to which. And the answer is as follows. So you have the real axis and the imaginary axis, and you have I pi, and you have some branch cut here, branch cut here. So let me explain which part corresponds to which. So now I'm going to use color. So let's draw this and draw this. So this green line corresponds to the region here, and this purple line corresponds to the region here, and this yellow line corresponds to here, and the yellow line comes here, and I don't know if this is orange. Okay, this orange line comes here. Okay, it's beautiful. So this whole region is mapped to this strip. Okay? Well, this is just like if you're not convinced, then you can probably play with Mathematica later and confirm this statement. Okay. So this was just like a change of variables. And now I'm really going to bootstrap these S matrix. So to bootstrap the S matrix, I need to impose some consistency condition, which I call axioms. So the first consistency condition that I need to impose is the unitarity of the S matrix. So what is the unitarity of the S matrix? Unitarity of the S matrix basically means S times S dagger equals 1, because the probability is conserved. And in the language of theta, you can actually express it in this way. S theta times S minus theta, these are matrices. And this dot is basically matrix multiplication, is proportional to the identity matrix. And well, okay, so in some cases it's kind of easy. So let's assume that S of theta is living here, which corresponds to theta being here. Then S dagger of theta, or the S, like a conjugate of that S matrix, amounts to computing the S matrix here, which corresponds to here, right? And they are related by theta going to minus theta. And essentially, this equation is coming from that requirement. So, oops. These are conjugate. Now, there is yet another constraint coming from the crossing symmetry. So essentially, the crossing symmetry is the statement that I can view the scattering process in this direction or in this direction, but the answer should be the same. And in the language of thetas, it's essentially saying that Sijkl theta is the same as Silkj of I pi minus theta. Let's see if I can explain this. So the left-hand side, which is Ijkl, is like is coming from viewing this S matrix in this way. And the right-hand side is coming from viewing this S matrix in this way. IL is incoming and Kj is outgoing. Kj's are outgoing. Okay? And finally, I need to impose the Mbox equation because I claim that this system is integrable. I think in terms of complexity, unitarity is the easiest, and the Mboxer, well, I mean, from the conceptual complexity point of view, I think unitarity is the easiest, and the Mboxer is the most complicated. But I'm going to proceed in the opposite direction. So I first impose the Mboxer, and then impose crossing, and then impose the unitarity. That's what I'm going to do. But before doing so, let me introduce some nice pictorial notation for the S matrix that I was using. So I was using this notation. Now it's a function of theta. So now each indices runs from 1 to n, and there is ON symmetry. And there is essentially 3 different ways to write down the tensor structure, which is consistent with the ON symmetry. So let's factor out the overall factor. And the first, okay, so let me first write the formula and then explain. Ik JL plus B theta IJ KL. So this picture basically means the delta function IL and JK. So this is one ON invariant tensor that you can write. And on the other hand, this basically means the tensor IK and JL. And this is tensor IJ KL. So these are 3 structures that you can write, which is consistent with the ON symmetry. Okay, and I factor out the overall scalar factor and denoted by theta, and the relative factor between the first and second will be denoted by A of theta, and the relative factor between first and the third will be denoted by B of theta. Okay. Ah, that's a good question. I just forgot to erase. Okay. The second line? The first line? Ah, okay, it doesn't really matter because I'm not really talking about some physical process in which IL goes above JK. It's just like a way of contracting the indices. Okay, so now I can use the advantage of using the colored. So now what I'm going to do is to impose the Mbox equation using this pictorial notation. So Mbox equation. So I'm going to explain two different Mbox equations, which are independent of each other. So the left-hand side of Mbox equation is something like this, right? If you remember. So you have P1, P2, and P3, right? And I'm going to assume that I have one index, which I denote by this color, coming in from here, and then the same color is coming out from here. So this is one configuration that I can think about. And then I also use two different colors, two different indices. So now I assume that this black index is coming from here, and it's going out from here. And there is yet another color that I'm going to use. So this green index is coming from here and going out from here. And now the task is to just connect these colors consistently. And it turns out, okay, maybe I should ask, well, how many possibilities can you think of to connect the incoming colors and outgoing colors? Okay, the answer is one. So I don't know what is the good way to explain that point, but okay, so let's talk about green color. So then the green color either goes like this, or maybe it might go like this, right? But if the green color goes in the left path, goes along the left path, then now it becomes impossible to connect the purple color. So which means that the only possibility P3 can take is, okay, now I'm going to use this, is this one. Once you understand it, then it's immediate that there is only one possibility because you can only connect in this way and you can only connect in this way, right? Okay, so now you see three different scattering and the indices go in a different way. Let's try to compute this S matrix. So here, so let's focus on here. So here I have this one, right? So I basically just get, okay, so I should first say that actually, let me see. Okay, so I wrote three functions, sigma, A, and B, but actually Mbox doesn't give any constraint on sigmas because the Mbox is basically telling us that this is equals to yet another configuration, sorry, yet another picture, but essentially on both sides, sigma appear in the same way because it's the overall factor. So the Mbox doesn't give any constraints, so we can just forget about it. So for now, I'm going to set sigma to be 1. So if you set sigma to be 1, then because in this scattering, I'm using this part, so I can just simply put 1 here. And let's now discuss this part. So now here P2 and P3 are scattering, and the pattern of the scattering is this one, right? A of sigma, A of theta. So what I get is A times theta 2 minus theta 3. And finally I have this. So here P1 and P1 and P2 are scattering. And the pattern of the scattering is again this one. So I have theta 1 minus theta 3 here. Okay? So this is the left-hand side. Now let's equate this with the right-hand side of the Mbox equation. I should use the same color. Here I have this one. Here I have this. No. I have this, this. Okay, so now one way to connect these lines is to do something like this. And for the purple, I should do something like this. Great. And then for the black, I should do something like this. Okay, so then here I have 1. And here I have scattering between P1 and P3, so I should have A theta 1 minus theta 3. And here I have a scattering between P2 and P3, so I should have A theta 2 minus theta 3. Sorry, I think I did something wrong. Yes, there's one more, but I think at this stage I already did something wrong. Okay, actually I did something wrong on the left-hand side. So here, so the second factor is actually not theta 1 minus theta 3, it's actually theta 1 minus theta 2. Because if you follow the trajectory of the particle, here I have a scattering, between P1 and P2. Okay? So so what I said is that here I have, so this part is correct, so I have something like this. But yes, as somebody said, there is yet another scattering on the right-hand side. Unfortunately, I need to go to the other page, but okay, so let's draw yet another one here. So the yet another one is like this. So you have purple coming here, and then going out like this, and then black is coming from here, and then going like this, and then green. So did I use green? Yes. It's going like this. And now 1, 2, 3. So here I just get 1. Here I get A times A of theta 1 minus theta 2. Here I get A of theta 1 minus theta 3. So let's add that. So this means that I have this factor. Let's add this factor. Okay, sorry, I forgot. A theta 1 minus theta 2. A theta 1 minus theta 3. So this is the functional equation that you need to solve. And it's actually easy to solve. You can actually show easily that this is equal to this equation. If you divide both sides by all possible a's that appears in the formula. And this equation is basically telling us 1 over a. So you should look at the arguments of a's. So here I have theta 1 minus theta 3. Here I have theta 1 minus theta 2, and theta 2 minus theta 3. And the point is that theta 1 minus theta 2 plus theta 2 minus theta 3 is theta 1 minus theta 3, which basically means 1 over a theta is linear in theta. So this is some unfixed coefficient. Okay, so this is the consequence of the first Mbox equation. And let me, but okay, so far I only constrained A's, but you probably want to get the constraint also for B. So Mbox 2. So for that, I need to consider yet another configuration. So, but let me just, this time, let me just draw the final answer. So now I'm going to consider this kind of configuration. And here I have this. And let me not use the color because it takes time. So I'm going to consider this configuration. So now there is actually only one way to connect the colors. And like this, and 1, 2, 3. And so now I have some different type of scattering here. And this is precisely B-type scattering, B-theta scattering. So in this way, I can get some information about B's. So I have some B of theta 1 minus theta 3 times A of theta 1 minus theta 2, which comes from here. So this is the left-hand side. And then I also need to draw the right-hand side. And again, there are two different configurations. And one configuration is something like this. And the other configuration is something like this. And I have this. And here I again get B. But now B for B. Now what I get is B of theta 2 minus theta 3. And then I have A of theta 1 minus theta 2. So now here there is yet another one, as I said. So, okay, so I have purple here, and I have black going in this way, 1, 2, 3. So now I have two B's actually, one here and one there, and the answer is B of theta 2 minus theta 3, B of theta 1 minus theta 3. Okay. Okay, so now I can divide both sides by a product of B's and A's, as before. And then I get this equation, A of theta 1 minus theta 2 equal, essentially this term is coming from this term after the division, and is equal to 1 over B of theta 2 minus theta 3 minus 1 over B of theta 1 minus theta 3. Okay. And we already know what 1 over A is, and 1 over A is C times theta 1 minus theta 2. And what we need to do is to solve this equation. But again, the solution to this equation is very simple because theta 1 minus theta 3 minus theta 2 minus theta 3 is theta 1 minus theta 2. So which basically means that 1 over B theta is minus C times theta plus D. And this constant shift cannot be fixed because the expression that appears on the right-hand side is the difference. Okay, so in this way, we could determine A's and B's up to some constants. So let me write summarize the results so far. So I have some overall coefficient which is unfixed, and then I have this crossing, I, J, K, L, and then I have 1 over theta times theta, C times theta with this crossing, and then 1 over D minus C times theta with this. Okay, so of course this is not everything that we can get. I can impose yet another configuration for the Mbox equation. And this is actually exercise problem, which you can find on the web page. And if you solve this Mbox equation, you know that D is actually given by n minus 2 over 2, where n is the n of the ON model. Well, as you can see, this is a bit non-trivial statement because the n appears in the formula. And, but that point is explained in the exercises, in the exercise problems. And okay, so then after imposing that, we also need to impose 2 more constraints, or 2 more axioms that I talked about. And one is the crossing symmetry, which basically says that Sijkl theta is Silkj I pi minus theta. Well, if I write with indices, it looks a bit complicated, but essentially the crossing symmetry is telling us that I can look at this S matrix in this way or in this way, right? It's essentially related by 90 degrees rotation. And if you do the 90 degrees rotation, you discover that essentially this tensor structure and that this tensor structure gets swapped. And because of that, if you look at this crossing equation, then you get the constraint like this: 1 over d minus c theta, this is the left-hand side, equals 1 over c times I pi minus theta, right? And this basically determines d, c. Well, we already determined d, so we determine c. C is essentially d over I pi. Or in other words, d is I pi times theta, I pi times c. Yes?
I have a look at your exercise later, but can you give a way you think about how Mbox equation knows n? It just seems like 6 is a frequency and...
Okay, so what gives you n? So, okay. Yes, I'm willing to answer the question, but at the same time, I don't want to spoil the exercise. But okay, so well, actually, I think there is a hint in the exercise problem, which explains that point. Yes. Okay. Yes, so yes, what the mistake that I did was, I think this, I was using some weird, I think in the original one, I think I was doing correct, right? Let's go back. Okay, here, I got it correct, no? Okay. Yeah. Okay. But I think essentially the analysis, well, you can well, I understand what your point. Well, let me see how to easily fix this problem, but yeah, okay, so the index is complicated. As you can see that I made a mistake, but essentially the whole point of the crossing symmetry is basically a statement that you can look at S matrix in this way or in this way. And I think this is not ambiguous. Thanks for pointing that out. Okay. All right, so, and finally, I need to impose the unitarity. But okay, so before going to unitarity, I also need to say that the crossing symmetry also gives some constraint on sigma, because now sigma also needs to satisfy this equation. Right? Okay, so now I need to impose the unitarity, and remember that the unitarity is something like S of theta times S of minus theta is 1. And this basically gives some constraint of sigma, and if you work it out, then you get this expression. Where delta is 1 over n minus 2. And together with, so now I have some functional equation for sigma. So one is this guy and the other is this guy. And so another exercise problem is to solve these functional equations. And if you solve it, then you can actually determine the functional expression for sigma, which is some gamma function, the ratio of product of gamma functions. And the reason why you get gamma function is because this crossing equation involves the shift by I pi, and typically if you want to solve the equation which involves the shift, then you get the gamma function. Okay, so I should also say that similar functional equation you will encounter also in lecture 4, the final lecture, hopefully, if I made it. Okay, so that's the end of the first lecture. So is there any questions so far? Yes?
I think that shape is n equals 3, it's singular, right?
Yes.
So it's just a participating circle. So it's
Yeah, so because it's free, so there is nothing to scatter, right? Like a sigma model.
solution is sigma
Yeah, so yeah, but we should also remember that I was already using 3 different colors to derive those different equations. Yeah, so everything breaks down actually.
Is other questions?
So, by the way, how do you know they are the unique solutions?
Oh, that's a good point. Actually, it's not unique. But, well, it's not unique. Okay, in particular, this overall phase factor is not unique. So because typically functional equations have several different solutions. But this is the one which have the best analytic property and also which have the simplest answer. And you can actually check the answer by comparing the answer with the large N expansion.
Anyone else? No? All right, now let's thank Shota for the beautiful introduction.